Grab a globe, or just pull up a map on your phone, and look at South America, then look at Africa. Now tilt your head a little and really look. Those two coastlines fit together. The bulge of Brazil tucks neatly into the Gulf of Guinea like two jigsaw pieces that got separated. It's not subtle. It jumps out at you. This is not a trick of the eye. Cartographers noticed it almost as soon as European ships mapped both coasts, in the 1500s, not long after those voyages of discovery. In 1596, a Flemish cartographer named Abraham Ortelius wrote that the Americas had been torn away from Europe and Africa and pointed to the matching coastlines as evidence. He was not taken seriously. For the next 3 centuries, nobody was. What would taking it seriously even mean? That Africa and South America were once glued together and then somehow drifted apart across thousands of miles of open ocean? That's absurd. Continents don't move. Continents are the most permanent, massive, immovable things on Earth. Solid rock, thousands of meters deep. The idea that they could wander across a planet. You'd have to be some kind of crank to believe it. And yet, this is the story of an idea so outrageous that the world's scientific establishment didn't just disagree with it, they laughed it out of the room. And then, a generation later, quietly admitted it was right. It's a story about evidence and mechanism, about what it takes to convince science of something true, and about how science eventually self-corrects, even when the correction takes half a century. It begins in 1910 with a German meteorologist staring at a world atlas, a man most of the world had never heard of, who was about to become the most argued about scientist of the century. His name was Alfred Wegener. Alfred Wegener was born in Berlin in 1880. He trained in astronomy and meteorology, not geology, not earth science. He was an outsider to the discipline he was about to upend. That fact mattered enormously, and we'll come back to it. By profession, Wegener was a polar explorer and weather scientist, the kind of person who wintered in Greenland and launched weather balloons into Arctic gales. Methodical, tough, and not easily deterred. In 1910, he was paging through a world atlas when the South America-Africa fit stopped him cold. He later described it as an observation he couldn't shake, one that kept pulling him back. He spent 2 years gathering every piece of evidence he could find before going public. In January 1912, he stood before the Geological Association in Frankfurt and presented his theory: the continents had once been joined as one. He called this ancient supercontinent Pangaea, from the Greek for all Earth. About 300 million years ago, he argued, it was one vast piece of land surrounded by a single world ocean he called Panthalassa. Then it broke. Over hundreds of millions of years, the pieces drifted slowly toward where we find them today, and they are still moving. He published his full case in a 1915 book, The Origin of Continents and Oceans. It drew on evidence from geology, paleontology, and climate records, 4 separate lines of evidence, all pointing the same direction. The coastline fit was just the opening move. Let's walk through the real evidence. Because this is where the story gets interesting. The first and most dramatic line of evidence: fossils. Identical ancient species found on continents now separated by thousands of miles of deep ocean, species that could not possibly have swum across. Consider a small freshwater reptile called Mesosaurus. Its fossils are found in a specific geological formation in South America, and the identical formation in southern Africa. Mesosaurus lived in fresh water. It couldn't have crossed an ocean, so how did it reach both sides? The standard explanation was land bridges. Vast strips of continent that had supposedly sunk into the ocean, letting species migrate and then conveniently disappearing. Very tidy, very unverifiable. Wegener found land bridges intellectually dishonest. You could draw one wherever you needed one and call it an explanation. Continental drift accounted for all the same data with a single mechanism. His second line of evidence: the rocks. Mountain ranges on opposite sides of the Atlantic matched almost perfectly in age, rock type, and structure. The ancient Appalachians of eastern North America continued seamlessly into the mountains of Scotland, Ireland, and Norway. These were vaguely similar ranges. The rock formations were essentially identical, down to the minerals and age. You wouldn't expect that from 2 unrelated mountain chains on opposite sides of an ocean if they hadn't once been one chain. Third, ancient climate. Enormous coal deposits, which form only in warm, wet tropical swamps, had been found in Antarctica, one of the coldest, driest places on Earth. How does a tropical swamp end up at the South Pole? And the reverse was equally strange. Ancient glacial scars, deep scratches left by moving ice sheets, had been found in southern Africa, India, and South America, all in regions that are warm or tropical today. The ice flow directions in those scratches only made sense if those continents had once been joined near the South Pole. Reassemble them, and the arrows converge, pointing inward to a single ancient ice cap. Fourth, And perhaps most compelling, a plant called Glossopteris, a seed fern whose fossils turned up on 5 separate continents: South America, Africa, India, Antarctica, and Australia. All of them. Glossopteris couldn't float. Its seeds couldn't blow thousands of miles across open ocean. It appears on 5 land masses simultaneously because, when it was alive, those land masses were one coastline fit, matching fossils, matching rocks, coal at the South Pole, tropical glaciation scars, a fern on 5 continents. Wegener thought no single alternative explanation could account for all of this at once, only drift. In many ways, he was right. The evidence was real, carefully assembled, and genuinely impressive. So why did the scientific world respond with something close to contempt? The answer has 2 parts, one that reflects badly on science, and one that is actually a feature of how science should work. When Wegener's book was translated into English in the 1920s, it triggered a storm in geology. British geologists were dismissive. American geologists were outright hostile. Part of the hostility was professional. Wegener was a meteorologist, not a geologist. He was proposing to overturn a field he hadn't formally trained in. That made geologists prickly, and not entirely without reason. Scientists are human beings, and expertise matters to them. An outsider sweeping in to declare that the solid, immovable ground beneath everyone's feet is secretly wandering, that takes enormous audacity, or enormous evidence, preferably both. A major symposium in 1926, organized by the American Association of Petroleum Geologists, gathered leading geologists specifically to evaluate continental drift. The verdict was nearly unanimous, the evidence was insufficient, and the theory was not geology. But buried in the professional snobbery was a deeper objection, a genuinely good scientific objection. Wegener's theory had no mechanism. He could argue powerfully that the continents had moved. He could not explain how. What force in the universe could push billions of tons of solid rock thousands of kilometers across a planet? Wegener proposed 2 candidates. First, centrifugal force, the spin of the Earth flinging continents toward the equator. Second, tidal forces from the moon and sun pulling the continents westward as the Earth rotated. Physicists calculated both. The centrifugal force available was something like 1/1,000,000th of what would actually be needed to move a continent. The tidal force was even smaller. The numbers were laughably, embarrassingly wrong. This wasn't a minor quibble. In science, beautiful evidence is not enough if you can't explain how the thing happened. A good mechanism is not optional. It is the difference between a hypothesis and an explanation. Without a mechanism, accepting continental drift was like believing in a magic trick. The continents had moved, but nothing moved them. And most scientists, quite reasonably, would not believe in a magic trick. So the theory sat, argued over in some parts of the world. South Africa and some European countries never quite abandoned it, but largely dismissed in the English-speaking scientific mainstream. Wegener spent the rest of his life defending his idea and doing the field science he loved. He kept refining the evidence, corresponding with scientists, publishing revisions. He never abandoned the theory, but he never found the mechanism either. In 1929, he published a final revised edition of his book, strengthening the geological case, tightening the geography of Pangaea, extending the timeline. The mechanism gap remained. He believed the evidence alone should be enough. In the spring of 1930, at age 49, Wegener led a major German scientific expedition to Greenland, his 4th Arctic expedition. Its goal was to establish a year-round weather station deep in the ice sheet interior. The expedition ran into severe trouble. The interior station was desperately undersupplied as winter closed in, temperatures dropping to 60 below zero. Wegener volunteered to lead the emergency supply run himself. He reached the interior camp on November 1, 1930, his 50th birthday. He spent one night, handed over the supplies, shared a birthday celebration with the stranded team, and set out to return across the ice sheet. He never made it back. Wegener's body was found the following spring, carefully buried in the snow by his traveling companion, a young Greenlandic man named Rasmus Wilhelmsen. Wilhelmsen himself was never found. Alfred Wegener was 50 years old. His theory was widely rejected. The discovery that would prove him right was still 3 decades away, in an ocean he had never studied, using technology that did not yet exist. It is one of the great tragic irony stories in the history of science. The man who got the big idea right, perhaps the biggest idea in the history of Earth science, died dismissed, on the ice, unvindicated. For the next 2 decades, continental drift was treated as a fringe idea in most of the scientific world. Geology was taught without it. The textbooks moved on. The puzzle pieces of South America and Africa remained officially unexplained. But the ocean floor was hiding a secret, one that would change everything, and it would take a world war and the technology that came out of it to reveal that secret. During World War II, navies mapped the ocean floor with sonar, sound pulses that bounce off the bottom and measure depth. For the first time in history, humanity could see what was actually down there. The ocean floor wasn't the flat, featureless mud plain everyone had assumed. It was as rugged as the continents, mountains, trenches, plains, and it was dominated by one feature nobody had expected. Running through the center of every major ocean basin and connecting into a single continuous chain was the longest mountain range on Earth. We call it the Mid-Ocean Ridge System. It stretches over 65,000 kilometers around the entire globe. Nearly all of it is underwater. It had been invisible. Piecing it together required years of painstaking work by an oceanographer named Marie Tharp, who plotted thousands of sonar data points by hand to produce the first systematic map of the ocean floor. Tharp noticed something in the data that nobody had seen before. Running down the spine of the Mid-Atlantic Ridge was a deep central valley, a rift. She recognized it as a zone where the crust was pulling apart. Her finding was initially dismissed, but earthquake records confirmed it. The entire rift zone was seismically active, one of the most earthquake-prone regions on Earth. Something dynamic was happening there, something fundamental. Enter Harry Hess, a Princeton geologist who had served as a U.S. Navy officer during the war and used his command ship's sonar to quietly map the Pacific seafloor on the way to battles in the Pacific. In 1962, Hess published one of the most important papers in the history of geology. He called it, self-deprecatingly, an essay in geopoetry. Its title, History of Ocean Basins. His idea, the mid-ocean ridges, are where new seafloor is being manufactured. Molten rock from the mantle wells up at the rift, erupts, cools, and then spreads outward in both directions, like a slow conveyor belt moving away from the ridge in both directions. This meant the ocean floor is not ancient. It is constantly being born at the ridges and slowly moving outward, carrying whatever sits on top of it, including continents, and at the far edges, where spreading crust reaches a continent. It doesn't pile up, it dives. It sinks back down into the mantle in a process called subduction. The old crust returns to the depths. A perfect, planet-wide recycling system. This was the mechanism. Not centrifugal force, not tidal pull. The engine was inside the Earth all along. Heat-driven convection in the mantle. The slow churning of rock so hot it flows over millions of years, like extraordinarily thick syrup. Wegener's great unanswered question, what could possibly move a continent, finally had a real answer. The continent doesn't push through the ocean. It rides on the ocean floor, like cargo on a conveyor belt. It didn't even know it was there. An elegant mechanism, but science needs more than elegance. It needs evidence you can measure, and the decisive evidence came from magnetism, from something strange baked into the ocean floor itself. When molten rock cools, tiny magnetic minerals inside it align themselves with Earth's magnetic field at that moment. Like billions of microscopic compass needles all pointing the same direction, then locked in place as the rock hardens. Here's the key fact. Earth's magnetic field has flipped many times throughout geological history. North becomes south, south becomes north. Each reversal is gradual, taking thousands of years, and every flip is permanently recorded in the rocks that cooled during it. Now apply this to seafloor spreading. If new rock is continuously forming at the ridge and spreading outward, each batch of fresh rock should carry the magnetic signature of the field at that moment. As the field reverses over time, you'd get alternating stripes baked into the ocean floor. And, crucially, the pattern should be symmetric. The same sequence of reversals on both sides of the ridge, like a mirror image, because crust spreads equally in both directions. In 1963, two researchers at Cambridge, Fred Vine and Drummond Matthews, published a paper making exactly this prediction and connecting it to seafloor spreading. If Hess was right, these symmetric magnetic stripes should exist. A Canadian geologist named Lawrence Morley had independently arrived at the same hypothesis and tried to publish it first. His paper was rejected, twice. One rejection reportedly suggested his idea was better suited to informal discussion than to a scientific journal. Today, the hypothesis is sometimes called Vine, Matthews, Morley in acknowledgement of all three. Science doesn't always credit the right person at the right time, but it usually gets there. The prediction was specific and testable. Research ships towed magnetometers across the ocean floor and measured the magnetic field of the rock below. And the stripes were there, perfectly symmetric, perfectly matching the known sequence of magnetic reversals. You could even date the stripes. Because the timing of magnetic reversals was known from other rock records, you could read the age of the ocean floor directly from the stripe pattern, like reading growth rings in a tree, only the tree is an entire ocean. This was a smoking gun the seafloor was spreading. The mechanism was real. The ocean floor was a tape recorder of Earth's own magnetic history, and humanity had just learned to read it. By the mid-1960s, the pieces were all in place. Researchers combined seafloor spreading, magnetic stripes, earthquake patterns, and ocean floor age data into a single unified framework. They called it plate tectonics. The idea, Earth's outer shell, the lithosphere, is broken into roughly a dozen major plates and several smaller ones. These plates float on the slow-turning mantle below and move relative to each other, constantly, over geological time. Plate tectonics isn't just continental drift with a new label, it's a complete explanation for why almost everything geological happens where it does. Earthquakes, volcanoes, mountain ranges, ocean trenches, all of them. Earthquakes happen where plates grind past each other, collide, or pull apart. The San Andreas Fault in California marks where the Pacific Plate slides northward past the North American Plate, a boundary you can hike along. Most of the world's volcanoes sit above subduction zones, where one plate dives beneath another and the descending rock melts and rises. The ring of fire around the Pacific is simply the outline of the subducting plate surrounding it. The Himalayas, the tallest mountains on Earth, formed when the Indian subcontinent collided with Asia and crumpled both edges upward. That collision is still happening. The Himalayas are still rising. One framework, one mechanism. Explaining all of it. It was a unifying revolution for Earth science, comparable to what Darwin did for biology, or what Newton did for motion. And what does all of this mean for Alfred Wegener? By the late 1960s, there was essentially no scientific debate remaining. Continental drift, his core claim, had been right all along. The mechanism he proposed had been wrong, but the idea that drove the whole enterprise was vindicated. He died in 1930, dismissed and largely forgotten. The sonar technology that would have saved his theory didn't exist yet. The magnetic stripe evidence wouldn't be collected for another 30 years. He never knew. The irony is almost perfect. The tools that vindicated him came from a world war that ended 9 years after his death. The researchers who proved him right were born after he first published his theory. Today, plate tectonics is one of the most thoroughly confirmed theories in all of Earth science. It predicts where earthquakes will occur, where volcanoes will erupt, where oceans form and continents grow. And it all traces back to a meteorologist with an atlas and an uncomfortable feeling that two coastlines didn't belong apart. Here's the part I want you to hold on to. The continents are moving right now, at this exact moment, as you watch this. As you sleep tonight, they never stop. How fast? About 2 to 5 centimeters a year, roughly the rate your fingernails grow. Patient, relentless, and completely unstoppable. The Atlantic Ocean is getting wider. Australia is drifting north toward Asia. The African plate is slowly splitting apart along the Great Rift Valley. In 50 million years, the map will look nothing like what you know. Some geologists project that the continents may eventually reassemble. Another Pangaea, perhaps 250 million years from now, the Earth cycles through supercontinents the way a wave cycles through ocean swells. And Alfred Wegener, the meteorologist who stared at the map and refused to accept that two coastlines fitting together was a coincidence, his fingerprints are on all of it. His story is also science's story, about how evidence and mechanism together are more powerful than either alone. About how the establishment can be wrong without being dishonest. They needed a mechanism, and that was fair. About how science eventually self-corrects. The scientists who rejected him weren't stupid or corrupt. They were doing their jobs. When the mechanism arrived, when the sonar maps and the magnetic stripes and the earthquake patterns all clicked into place, they changed their minds. That's exactly how it's supposed to work. Even if it took 50 years. The ground beneath your feet is moving. It has always been moving. Somewhere out there right now, another Wegener is looking at data that everyone else is ignoring, seeing a pattern that the world isn't ready to believe yet. That's worth staying curious for. Thanks for being curious with me today. If the ground feels a little less solid than it did 20 minutes ago, good. It was never quite as solid as it looked. Until next time.